can actually have. That's like provide both outside the categories. Let's get started. Now, so today we will talk about heap exploitation. This is a technique used in the real world right now, not only at the user space level, but also kernel level. Kernel has its own heap. User space, usually we're talking about the C library, glibc heap. So not only C programs will use this library, some other programs, even Python programs, they may eventually call C programs, so they will also use heap or even the same heap. So we will spend some time talking about what is heap, or another name for it, dynamic memory allocator. So usually we're talking about the same thing, heap or dynamic memory allocator. Then we will talk about the malloc and free interface. Then we talk about particular Tcache implementation of heap. That is what we currently use on our server on most of your systems. Then we talk about how we exploit those vulnerabilities. We will discuss overflow. We will discuss use after free. There are many other attacks as well, like double free. We will also talk about them briefly. But heap is actually a beast. We can spend half a semester just talking about heap exploitation. So today we are not going to dive that deep. So this is a memory map you are familiar with. We talked about this since the very first class. So this is a traditional 4 gigabyte Linux 32-bit machine memory for each process. 64-bit will be similar, but things could be moving around at different areas. They may have different size, right? So at some lower level, but obviously not at the very first page, memory 0, because 0 is reserved for, it cannot be used. Right? Then we have the text section, we have data segment, usually the .data section. We have BSS segment. They are used for uninitialized local global variables, and C require them to be initialized to 0 at runtime. Then the data segment has initialized global variables. Then we have the heap, right? Then we have the libraries, we have stack, and higher space we have kernel memory. So kernel memory is mapped in user space processes, but they do not necessarily have the permission to access it. If you are interested in why they are mapped, then you should take the operating system test. So what I talk about here is the heap. So some of you have implemented your own memory allocator from maybe 3650 computing system class, right? You allocate a simple memory allocator, and then you use that allocator to replace the glibc allocator, right? So usually we use different system calls to ask for a huge space. Then we manage that big space. The system call can be brick, sbrick, or memory map. And the end of the heap is something we call a program brick. That's why the system call is also called brick. Then the beginning of the heap is the start of the brick. So heap goes from low address to higher address, and the stack goes from higher address to low address, because in stack we use the push. Every time you push, the stack goes from higher address to lower address. So heap is basically a pool of memory used for dynamic allocation when you run the program. So it is different from the stack memory because it is persistent between functions. stack memory are used for the stack frame, local variables, return address, temp variables. One function may have multiple local variables, and every time you invoke that function, there is a copy of that local variable. So there could be many copies of that local variable. And they're at a different address. They're not really the same thing. And when that function returns, that stack frame is recycled. ESP, RSP will move from a lower address to a much higher address. So that the stack memory is basically recycled. So those local variables, they are not really persistent between functions. There are some local variables. They look like local variables. For example, you can define a local variable as static, right? But those are not really local variables. Those are implemented as global variables. Okay? So they are not really on stack. So heap is totally different memory region, as we saw in the previous figure. So heap is not on stack. And so it doesn't have to be recycled when a function returns, when a function exits. So they can be persistent. So in the C standard, we define multiple interfaces for programmers to ask for memory. We can use malloc, we can use free. Those are C functions, and they are not system calls. Okay? There are no system calls directly to those C functions. So a lot of system functions you have been using in this class, change mod, open, send the file. There are C library functions for that. And those C library functions eventually map to the same name system call. But those two functions, they are just the C library functions. They are not system calls. Of course, in other programming languages, you have different interfaces. In C++, you can use NEU to create a new object, and that will be on a heap. You can use delete to delete that, to recycle the heap memory. Other programming languages, Python, they will have the similar things, and they may eventually use the same C library function to do that. So then there are system calls for us to allocate memory. Okay, then why don't we directly use those system calls? Instead, we need those C library functions. First of all, the OS provide at least 3 interfaces for us to ask for new memory, adjust the size of heap. One is memory map. You can ask for at least, you can also use the sbreak or break system call to ask for just a little bit memory. Okay, so technically you use sbreak. I think you use sbreak, you can just ask for several bytes. So, but the problem then is it's very expensive because they are system calls. When you make a system call like that, you need to go to the kernel, and the kernel needs to allocate new page tables, allocate the new memory for you. And if you're only asking for just several bytes, then that's too expensive. So what usually we do is the program will ask for a relatively big, large of memory for you, like 1 page, 4 KB, or 4 megabytes. Then the dynamic memory allocator, which runs in the usernet, will handle your future request for smaller memory pieces. So you develop a web server. Every time you get a request, HTTP request from the internet, the request could be 50 bytes. It could be 500 bytes. And every time you get a request, you need to copy that data from the network adapter eventually to your user space. So you need a memory for 50 bytes, memory space for 500 bytes, right? So every time you ask for that memory, you don't want to go to the kernel. It will be too slow. So your program will ask for 4 megabytes first, then manage that dynamically for you. So when you use malloc to do that, malloc will give you 50 bytes, give you 500 bytes. Instead of the malloc do not necessarily, every time you call it, it do not necessarily go to the kernel. You always manage that at username. So technically, you can use mmap break or sbreak to do memory management, but it will be too slow. It's not worthwhile because they can only allocate big pages or it's too expensive. So the idea is to use a dynamic memory allocator in the user space to do that. Of course, the kernel itself, they have their own heap or dynamic memory allocator, but that's a different story. But the implementation of that is similar to the implementation of the dynamic allocator in the user space. So user space, there has been many popular dynamic memory allocators. So DL malloc was a very famous one, developed in the 80s. And it was used by Linux for a long time. So right now, our Linux system uses something called the PT malloc. Yeah, it was based on the DL malloc and extended for multi-thread support. And it's part of the glibc library. Google has been implementing their own version of malloc for the TC malloc. If you took the CS3650, you have been developing your own malloc free as well. There is a professor at UMass Amherst, Emery Berger. He has been maintaining his malloc for years. Kernel has their own malloc, kmalloc. The interface in the kernel is also, it's not the malloc C function, it's a kmalloc kernel function. So Windows, iOS, they also have their own version of malloc. But a lot of ideas are very similar. So let's first take a look at those interfaces. 4 basic interfaces, and the most important one are just those 2. Malloc and free. So malloc takes 1 parameter of input. It's just how many bytes you want to allocate. Returns the address of that memory for you. So the interface is very simple. You ask the C library to give you several bytes of memory that is persistent. Persistent across functions, and it can stay there as long as your program doesn't exit. And you tell the C library how many bytes I need. Then the C library returns you the address of those bytes. That's it. Very simple interface. You do not really care about internally how it works. But as an attacker, obviously, we're going to study internally how that is implemented, then exploit that. The other interface is the free interface. It takes an address as input and will deallocate that space, put that space into the recycle bin, so the later malloc can reuse that space. So whenever there is a malloc, technically there should be a free. So users, developers, they're supposed to do that. And whenever you heard developers are supposed to do that, you know, that's a place that we can expect a lot of bugs, right? The developers may allocate a space, but forget about free it. So that is something called the memory leakage. So C programming language has this problem. Some other languages, they do not necessarily have this problem. They use something called the garbage collector to make sure if the memory is not being used, then there is a runtime garbage collector to deallocate that. Then the developers may malloc a place, then free it twice, right? A double free problem, or free it 3 times. So those behaviors are technically undefined, right? The standard doesn't say what should happen. Or if you malloc a place, some area, you get an address, but when you free it, you use a different address. The address you gave to free was not really mallocked, right? So that's another case. So all of that could happen. Developers can make those kind of mistakes. Attackers can intentionally do that to exploit the system. So besides the malloc and the free interface, there are two more interfaces. So first one is canlock. The interface of canlock can be the same as malloc, but I guess they intentionally made it a little bit different. It takes two parameters. The first one is the number of items. The second one is the size of each item. So you multiply them together, you get how many bytes you want. So I don't know why they choose this interface, but technically it's the same as malloc interface, how many bytes you want, right? So the real difference between canlock and the malloc is malloc doesn't set the memory to 0. It will only give you a piece of memory, a piece of buffer. Canlock will memory set that to 0, initialize that to 0. That's it. So technically you can do a malloc and manually set that to 0 by yourself. And another interface is realloc, and it takes a pointer as input and a size as input. So this interface will try to resize the memory block pointed by this pointer that was previously allocated by malloc or canlock. So you want to change the size of that. It will not always be successful. Sometimes it's not possible because this memory chunk, after that, the next memory chunk is already being used, so you cannot really resize them bigger. Then realloc will give you another memory region to use. Okay. So those are the 4 interfaces. So how to use them? I guess most of you are already familiar with this. We have a simple main function here. We have a local variable, which is a pointer, which we call it buffer. Then we allocate 100 in hex bytes, use malloc. So then if there is space, then this malloc will be successful and it will return the address to buffer. So under the hood, this is the first call to the buffer, to malloc. So the program may not have a heap yet. So under the hood, the first call, the program may need to make a function call to get some heap space. Then after that, many other calls will just stay in the user space. Then we can ask for some input from stdin, print it out. So after we use this, we just free this buffer. So malloc and free, that's a pair. That's the correct usage of that. So technically, here, after malloc, you should also check the return value, whether that's a valid address. If it's not a valid address, it means malloc was not successful. So you're not supposed to put that on there. So if we compare heap and stack, you can say stack has fixed memory allocation known at compile time. Right? So the heap variables, the local variables, their address is fixed. Okay, not absolutely, not fixed at any absolute address, but fixed at a relative address relative to where EBP is safe, right? Or RBP is safe. So that's why the local variables, they are addressed using RBP minus something or EBP minus something. Relatively to that, RBP minus something, that number, that is fixed. Okay. So those memory allocations were technically done at compile time. So we have local variables, return addresses, function arguments on the stack. So they are very fast. Okay. The allocation of those are very fast. Because everything is just an instruction. You have RSP, RBP, EBP saved on stack. Then the local variables is just directly accessed by an offset from that. That's it. Okay. So just one move instruction, you can access local variables. Another move instruction, you can write in data to that. So very fast, just several instructions. And it's also automatic. Developers, you do not really care about that. Say developers, you don't think about you need to make a special function call or whatever to create those variables. So it actually abstracts away the concept of allocation or de-allocation. Heap is different. Heap is dynamic allocation at runtime, and you can have all kinds of structures, objects there as well. Sometimes they are bigger than just a built-in say type. Of course, even local variables, they can be bigger than built-in say type. However, they will be slow. Why that slow? Because when you allocate a memory, you need to call malloc. Malloc is not an instruction. A full function. It's actually a very complicated function. Hundreds, thousands lines of code compiled into hundreds, thousands instructions. Sometimes it may involve a system call. When you heap enough, the program may ask for new heap memory, then it will make a system call to do that. Stack usually doesn't do that. If your stack is just not big enough, then your program will just crash. There is no better way to allocate more space for that because your stack will keep going down and down. If you use all the space, it will just crash. So also developers, it's developers' job to call those functions and call those functions in the correct way. So on our server, we actually use the C library version 2.31, which is ptmalloc 2. So why I talk about this version? Because this is a domain that changes very often. I think the latest version is probably already 2.4 something, 45 or 2.5. Okay. The interface stays the same. The implementation changes a lot. So this is a very fluid domain. A lot of attacks we learn today may not work tomorrow. So I think I mentioned a little bit last week. So when people discover new vulnerabilities in a specific version, then the next version try to fix that problem. But at the same time, it may make the stack run a little bit, the heap run a little bit slower. Then the next version of that, it will try to make it run faster and introduce new bugs. So later I will show you a link. You can see there are many different versions, and for each version, there is an example. A lot of example bugs, but they do not necessarily persistent for different versions. So the end of the heap is something we call a program break. Okay, remember that. So ptmalloc actually use memory map system call to get large memories. So I taught computing systems 3650. We have two homework for you guys in that class. One is implement the heap using the sbreak system call. Another one is use memory map to implement the heap. They are similar. So ptmalloc currently use mmap to do that. More modern. We do still use sbreak. So sbreak, if you pass 0 to that, it will return the current program break. It will tell you where it is, and you can expand the program break by smaller bytes. You can use sbreak or break to do that. Okay, so finally, we can talk about the implementation of ptmalloc 2. And there are also two versions of this. One is called tcache. Another is no Tcache. So the one we're using right now is the one with Tcache. But we will start with the version without Tcache, then move to the version with Tcache. So when you ask for a memory region, it could be a small one, right? 8 bytes, 2 bytes, it could be big, 1,000 bytes. Usually we're not asking for something like gigabytes. So if you ask for really, really big, you probably should use memory map directly instead of using malloc. So the memory that the heap or dynamic memory allocator returns to you, we usually just call it a buffer, right? But actually, internally, it maintains something called a malloc chunk. Okay. So the buffer it returns to you is part of this malloc chunk. So for those who implemented this before, since this will be very familiar, you probably choose a different design because we didn't tell you you have to follow any specific design. So then for every memory or malloc chunk, there are two states. One is it is free. It is in use. Free means it is available to be mallocked. In use means the program right now it is actually using it. So the ptmalloc implementation of this, the structure is called malloc chunk. The structure has two important fields here. Okay? This is the first field. The version doesn't really use this field. We will talk about this later. So the second field is actually the most important. The second field is chunk size. There is a memory chunk, and the second field tells how big is this memory chunk. And this memory chunk size is not the size the program asked for, the developer asked for. It's bigger than that. You ask for 8 bytes. There will be some overhead, right? There are some metadata we also need to store with that buffer. And this chunk size includes the size of the metadata. Then, after that, it's basically your data. That's a buffer. So when you do malloc, malloc returns you the address of this place after chunk size. The first field here is called chunk previous size. So in the ideal case, all the chunks, they will be next to each other. From the low address of heap, you have the first chunk, then you have your second chunk, the third chunk. There is no bytes wasted between the chunks. So the first field basically tells the size of the previous chunk. Okay. But the native version, we're not using this anymore. But the field stays there. We do not use it. It stays there. After that, it's just your data. Okay. That is when this chunk is in use. When this chunk is allocated, your data, what malloc returns to you, will be here. Okay? But if this chunk is not in use, the chunk is freed, the chunk is waiting for someone to use it to be mallocked, then we put other metadata here. Okay. So the no Tcache version, the other data, metadata include double link here. There is a forward link linked to the next available chunk, and a backward link linked to the previous available chunk. Okay. So only freed chunks, they are linked together using a double link in the older version. If they are larger size, there are also other pointers. So the blue block here, this is only used when this chunk is freed. When this chunk is in use, this is where user data is stored. Okay. we see many similar design success, not only just for memory, also for file systems. You want to chain them together. You also put metadata at the beginning. When that, let's say we have a hard drive and we have some blocks. If that block is in use, then we put data there. When the block is not in use, we need to chain them together in a freed block list, and we need to put more data there, right? The more metadata there. So when we use those metadata, we obviously want to put those metadata in the block. But when we use the block, then we don't have those metadata. So because malloc, the malloc chunk has to be there is an alignment. So usually for 8 bytes or 16 bytes. So the size can only be 8 bytes, 16 bytes, 32 bytes. The size cannot really be 5 bytes, 7 bytes. So the last 3 bits of that size doesn't really need to indicate the actual size. So they have other special meanings. They can indicate whether the previous chunk is in use, whether the chunk is obtained by memory map. Also, if this chunk belongs to a thread arena. So we will skip the concept of arena for this class. So anyway, in short, chunk, when we talk about chunk, we are talking about the beginning of the metadata. And the metadata has 2 fields. The size of previous chunk, which the latest version doesn't really use, but it stays there, and also the size of the current chunk. Then the buffer itself. So malloc actually returns you the address of this instead of the address of the chunk. Okay. So this is a double link there, but the current version do not use it. So also, even the no Tcache version, there are multiple beans for different sizes of chunks. Some chunks are for memory of 16 bytes. Some chunks are for memory of 32 bytes. Some are for 500 bytes. Okay. So when you allocate memory, allocator wants to find the available memory chunk for you as soon as possible. Right? So how do we do that? Instead of just maintain one big list, no matter it's double linked or single linked, we have maintain multiple lists. Okay? If you ask for 32 bytes, it will look for the list of available 32 bytes memory regions. It will not look for a bigger link which has 32 bytes, 500 bytes, 1000 bytes. That will be slower, right? So that's why there are some names for it. Fast beans, small beans, large beans. Also the top chunk is where it's a huge memory chunk that has not been divided into smaller chunks. There's another name for it. We will talk about that later. So that is the basics. So that is the PT malloc version, no Tcache. What we're using right now is something called Tcache. So this is a modern version. We're still using it. Tcache here basically means thread cache in malloc. And it is designed to speed up repeated small allocations in a single thread. Okay. So the size ranges, they are actually configurable. So when you design some infrastructure, so here, the memory allocator is an infrastructure will be used by developers, by applications. You need to understand how developers, how programs will be using your service, how they will be using your infrastructure. Right? So decades of study find out that most of the memory allocation requests are only asking for small memory regions, smaller than 1,000 bytes. So those are the most important requests. And there are so many of those requests, and we need to handle them. So the current design is the freed memory chunks, they are implemented as a singly linked list, not a double linked list. Then each thread has a header and a list of headers for different sized bins. There is a bin for size 16 bytes, 32 bytes, 48 bytes. Okay, there is a bin for each of those. Then for each of those, that's a header. Then we have a singularly linked list for all the available chunks. And the source code, the structure is defined like this. So there is a structure called tcache underscore per thread underscore struct. And this struct, first of all, it has some counts, and there are a number of bins. Each bin is for different size. Okay, so this field is not necessary, as it was explained in the source code comments there. Okay. A singly linked list. Technically, you just need to traverse that once, then you can get how many available chunks are there, right? This is just for performance. They were just store that. So as we say in the source code, the field is actually redundant. Then we have another field, which is also an array, and that is the entry. Okay. So that is basically the header or the head of each link, singly linked list. The whole thing is called a tcache pthread struct. And here we have the tcache entry. Remember this thing, tcache entry. So the previous design, we keep those two fields, previous size and size. We keep this previous size, but we don't really use it. Size one is very important. We use that. Then we do not have those free, those structures. We use them before when this chunk is free. All of these are replaced. They are replaced with just one tcache entry. That's it. That's just a pointer. Okay. So tcache entry, this is the structure of the tcache entry. It has a pointer to point to its own type, and it has another pointer to point to the tcache per thread structure. That's it, 2 pointers. The second one is called key. This is actually a security feature to detect double free. We'll talk about this later. Let's say one animation here. We have a thread. We call this thread bun there. Then this thread bun has a tcache pthread structure bun, and this structure has many different bins, right? We have many different counts there and many different entries. The first count here stores how many available malloc chunks with size 16 bytes are there. Okay. Entry is the pointer to the first chunk. The second one, we have how many malloc chunks with the size of 32 bytes are there. 32 here is actually the buffer size. Doesn't include the metadata. And the first pointer, then the entry is a pointer, points to the first chunk. Then we have 48 bytes, 64 bytes, up to 1,000 or even 2,000 bytes. So, and for each entry, they will have two fields. So as long as those malloc chunks are in the list, it means they are not being used, right? They are freed ones. They can be allocated. That's why they are here. That's why they are showing in this picture. So let's say if this malloc chunk serves 16 bytes, then from the entry may point to this guy, and this guy has another pointer points to the next available malloc chunk, and they have the second pointer, which is called the key, to point back to this per thread structure. So every freed malloc chunk, they have this pointer key back to this data structure. Okay, they have the same pointer there. The purpose of that is just to have some kind of random value to make sure we do not do double free. Okay, so let's look at this animation here. Assume we are here. This is a program counter right here. Before that, we have been malloc A, B, C, D, E, F, X, Y, Z. Okay. So A, obviously, are just addresses. They are pointers, addresses. First, we malloc 16 bytes, we get A. We malloc another 16 bytes, we get B. Then we get C, D, E, F, X, Y, Z. Okay. So at this point, we have those 9 malloc chunks, right? And they are in use. Okay. They should be somehow adjacent to each other if we view this as a linear, continuous memory address. But it's more convenient to draw them this way to understand how the linked lists work. So we don't really care if A is close to B or B is close to F. We don't care about that for this example. So now what we're going to do is, because they are in use, right? So we're not really using the next field or key field. The metadata, we still have two metadata fields, right? Previous size and the current size. And this is where malloc returns to the user. And because it's in use, we don't really have next or key fields. Now we are going to free B here. When we free that, it means this malloc chunk will be recycled. When we recycle it, we want to put it back to that P-cache, P-thread structure. So the later malloc will be able to use it. So when we free B, we will first check what is the size of B. It's 16 bytes. Okay. Then we put it back to this singular link, which means the count will be updated to 1. Now points to B. First and only item in this list. So the next pointer will point to just a null 0. Then the key will point back to the P thread state. Okay. The per thread structure point back to it. If we free A again, A has the same size. So A will be insert to the beginning of the 16 bytes list. Okay. And we'll always insert them at the beginning of the list. We do not insert them at the end of the list, because if you insert them at the end of the list, it takes the ON time, right? Because you have to traverse, because this is a single list, you have to traverse the whole list to find out where is the end, then you insert there. So it's always faster to insert at the beginning. That's why to free A, the points to A's key field points back to the entry. Next field points to B. Then we have F, which is a different size. F, a different bin. So F will go to the bin size of 32 here. Then E will also go to the same list. C will go to the same list. Also, the count here is updated to 3. Then D is a different size. D here is 48. That's why it goes to another list, another bin. So this is how it is implemented. So if we look at the source code, just the pieces of the source code, it will be it's actually very clear. So here we have the Tcache threading. So each Tcache entry, let's say on free, what happens is we first select the right bin based on the size. We know the size of the bin because where's the size of the bin? It's in the metadata, right? The current malloc chunk's size. Of course, that one included the buffer size and the metadata size. We just need to extract the metadata size, we get the buffer size. Right? The buffer size, -1 divided by 16, then we find out which bin we should use. So we have an index for the bin. So this is obviously integer, okay? So that's why we're -1. So if it's a 16, it means you should go to bin 0. Right? 16 minus 1 is 15. 15 divided by 16 is actually 0. Okay? So then we check to make sure the entry has not been freed before. If it was freed before, if it is already in the list, which means the key field where it points to the structure, right? So we use that. So we just check the second field for this. So the first field is the next field. The second field is a key field. We just compare if the key field is our per thread data structure. It means this is already in the free list. So we do not need to go through that singular list to check it if it is there, because that would be very slow. Of course, that is a very reliable approach. This is not a reliable approach. There may be errors. There may be attackers to put that value there, or this could just be a random value happen to be that address. That could happen, but the chance is very low. Okay. So this is basically a quick check to make sure this is not being freed twice. This malloc chunk is not in the free list. So this is a trade-off: speed, correctness, and security. This one is not necessarily always correct. Then we just push this or add this freed allocation to the front of the list. How we do that? So we put the current, this malloc chunk where we are freeing it. Its next field will go to the current head, whatever the head points to. Then the head will point to our current malloc chunk. Then we increment the number of count. That's it. Okay. So we inserted that at the beginning of the head. After that, we will change the key field to the pthread structure. Since double free means you free a memory area twice. We have a tag to show you later why this can be a problem. You can add arbitrary memory to the free list by doing that, basically. Then later, when a user or a program try to ask for memory, that memory should always come from the dynamic memory allocator, right? If you, as an attacker, can insert some memory chunks into that list, and later used by the program, it means you may be able to control what data is stored there. By double free, you can put them back into the list. There is an example to show that later. Okay, so the allocation is also similar. It's just a reverse. We first check how many bytes the program is asking. Then we know which bin we should look for. From the bin, we just check whether there is an available chunk we can use. Then we just reuse that chunk, and we always use the first one because that's fast. We only need to, it's constant time. We don't need to traverse the links there. So that's basically the code to do that. It doesn't really check. It will clear the key section, that field. If you do not click that, it cannot be free. It will also check if it can do all kinds of check, but the problem is if you add those checks, this will be very slow. This is already quite slow compared to stack allocation. Okay. So how many lines of code we're talking about here, and how big is our code base for heap? This is already quite slow. Okay, so if we, let's say, this is where we're at. So A, B, C, D, E, F, they are all free. That's why they are here in different free lists. Now, we do another malloc. If we malloc 16 bytes for this implementation, we are guaranteed to get the malloc chunk A, because it is the very first malloc for size of 16. When we do a malloc 32 twice, we are guaranteed to get a C first, then get an E second. If we do 8, then we'll get D. We do 16 again, we will get B, and 32 again, we get F. So that's a current implementation. So those are guaranteed. So if we ask for 64, right? We don't really have an available one for 64. So we're actually going to create a new one for it. So how do we create a new one? I talked about that before. We have a top chunk, which is big. We're going to split that top chunk into smaller ones. We actually only split them into 2 chunks. One is 48 bytes. Another one is the rest of it, still huge. Okay, then we are going to, 64. Then we are going to return the 64 bytes one to G. So later, it's free. This one goes back to that list. We do not necessarily merge them. Some older implementations, we actually merge them. Very complicated. Okay, one example here. This one will show us the chunk size. We have the main program. We're using malloc. We're using free here. You see, we didn't free. Okay, it doesn't really matter because the program exited here. So technically, we're not really leaking any memory. Okay. So we are mallocing 32 bytes, 4 bytes, 20 bytes, 0 bytes, 64, then all 32 bytes. We're going to print out the size of them, and we're using the G malloc, not our own version. We just call malloc. So this is a default C library version of malloc. We first malloc this 10 times. This for loop is just doing the malloc. Then we are going to another for loop 10 times. We're going to print out things. We print out 3 different things here. Print out malloc something at this address, this byte, and how many bytes to the next pointer. Okay. So what are we printing out? Print out the size. We mallocked. Okay. So that is the size in that array. Then we print out where the buffer is. Okay, 10 different buffers. We print out the address of each of them. Okay. Then we print out the distance between the buffer and the next buffer. Pointer I plus 1 minus pointer I. Okay? Just that. We print out that. So can you expect the output here? Good. So the first one, we malloc 32 bytes. Okay. Let's take that. Marker. So this is the beginning of the program. We have not been using the heap yet. Let's say this is a heap. This is high address. This is low address. At the very beginning, the whole thing is one big malloc chunk. Okay. One big, or big one. Let's say this is 4 KB. 32 bytes, several bytes, right? So the first malloc, we're going to ask for 32 bytes. So what is the size of the malloc chunk? 64, okay. Why do you think it's 64?
So you can put the metadata as well.
Okay, so how big is the metadata? 64-bit machine, how big is the metadata here? We have two integers. Each of them is 8 bytes, right? So, so that will be 16 bytes. So metadata and what we ask for could be 48 bytes. There could be some alignment to make it 64. That's possible, okay? But anyway, assume there's no alignment. So then we will have our very first malloc chunk here. Then this part, then we call it the top chunk, will be split into two chunks. Okay. The top chunk will still be huge, like this. The first chunk will be like this. There are two fields: the previous size, the current size, and the buffer. Okay. This could be 48 bytes. Then we ask for another 4 bytes. Okay. We ask for 4 bytes. We will still need the metadata, which is 16 bytes. Then split it again to two chunks. So this is the top chunk. This is the first chunk. This will be the second chunk. So the second chunk at least should be 4 plus 16 bytes, 20 bytes, right? But because of alignment, this probably will be 32 bytes. This probably will be 64 bytes. Could also be 40. So anyway, then there will be previous size, current size, the buffer. So here the buffer will still be bigger than what we asked for. We asked for 4 bytes. The dynamic annotator will give us a little bit more, just for alignments. The third one we can skip. The fourth one we ask for 0 bytes. Okay. What will happen?
So you get 16 bytes? So it'll still be 16 bytes?
Yes. So the interface actually allows you to do that. The interface doesn't. If you check the source code, there's comments saying that they actually allow this. So this will give you the minimum bytes. I believe it should be 16. 32-bit maybe 32-bit version maybe 8. So here is also maybe 16. So which means, of course, this will be third one. And the fourth chunk will be the same. Size, current size, then the buffer maybe 16 bytes. So they will be allocated one after another. Okay. Consequently. However, when you free them, it will be different. When you free them, you may free the second one first, the fourth one first, then the first one, the second one, the first one and third one are still in use. So how do you indicate whether it's in use or not? That's why you use a list to chain them together, right? Even though the first one and the fourth one, they are not together, but they are chained together through that list. So this is implemented the same way even for hard drive, secondary storage, when because in our computing system class, we also do a file system. So you did a similar thing for hard drive as well. So let's run this program. We have this program on our server. Chunk size. Let's look at 32-bit first. Oops. Okay. This is the result. The size of size T here is 4 bytes. The size of pointer obviously is also 4 bytes because this is a 32-bit machine. The malloc, the first malloc is malloc 32, and it returns us to that address A5B0. Okay, so that is the buffer address. That is not the malloc chunk address. Malloc chunk address is 8 bytes before that. Make sense? 8 bytes before that. Then the second one we malloc 4 bytes. So then this is the first one, this is the second one. By subtracting the second address to the first address, we get 48 bytes. Okay. So why do we get 48 bytes? We know the buffer at least 32 bytes. That's what we asked for. So it has to give us at least 32 bytes. Then we have 8 bytes of, no, I'm sorry. Not here. Because what we compute there, 40 bytes is not this 40 bytes, is the beginning of the first buffer to the beginning of the second buffer, right? That is the buffer of the first malloc and the metadata of the second malloc, right? And the metadata of the second malloc is 8 bytes. We know that, which means the buffer actually we get is 40 bytes here, right? So our own data is, for the first block, the metadata is also 8 bytes. So the reason we have this is because alignment. Okay. We ask for 32 bytes, we're actually getting 40 bytes. Okay. Then 0, the 1-0 is interesting. 0 and its address, so the address to the next pointer is 16 bytes. Okay. We asked for 0 bytes. The metadata will be 8 bytes. So it actually allocates 8 bytes for us. Okay. Which means the minimum allocation here is 8 bytes for 32-bit machine. So this one is interesting.
That probably just because of alignment?
Yes. Yeah, that's just alignment. I think I have a slide for that. Yeah, so this is a slide for it. Move this a little bit. The first chunk, 2 metadata fields, each of them 4 bytes. Buffer. Then the second chunk, and we know that from here to here, we know 48 bytes. We know this part is 8 bytes, which means the buffer is 40 bytes. Then let's look at the 64-bit version. I will just show you the slide. You can run this later. This one is very interesting. I keep telling you that for historical reasons, we have the previous size field, right? But in the modern version, we are not really using this field. Okay. So here, I show you an example that that field doesn't have special meaning and can be used as the buffer for the previous chunk. Okay, so we are asking for 32, 4, and 20 bytes, and 0 in this case. So the first chunk, we have 2 fields, metadata, total bytes. Then we have the buffer, we ask for 32 bytes. And the distance between the first one and the second one is 48, which means the metadata of the second chunk is 16 bytes. So the data for the first chunk is actually 32 bytes. Compared to the 32-bit version, we have 40 bytes. Now we have 32-bit. That's good enough. We only ask for 32 bytes. What interesting is chunk 3. Chunk 3, we ask for 20 bytes. Okay? But the distance between the chunk 3 buffer pointer to the chunk 4 data pointer, buffer pointer is 32 bytes. Okay. So from here, this is a chunk 3. This is a chunk 3 buffer pointer. What malloc return to you. From here to buff 4, it's 32 bytes. Okay. However, the metadata of chunk 4 is 16 bytes, 2 fields, right? So the buffer technically here is only 16 bytes. But we ask for 20 bytes. Right? Why would this work? It's because this previous size field, that 8 bytes, is not really used. There's no special meaning of that anymore. That's why this chunk can grow into the next chunk.
They allow that, why does the implementation maintain that previous size attribute?
Maybe the next version will just remove it. This thing changes so fast. Yeah,
it's so odd.
Yes. Okay, so like I said before, when the program runs for the first time, there is only one big chunk. We split them into smaller ones, right? That chunk we call it the top chunk or wiredness chunk. And the end of it is basically the end of the heap. When your heap is not big enough, you need to do memory map or sbreak to make it bigger. The size of that chunk will get bigger. That is also a chunk, so it follows the same format. And every time there is a malloc, and you cannot find a free chunk before that, you just split something from the top chunk, slice it into smaller ones. So malloc with 0 byte is actually a lot. If you read the source code, you can find that. In the comment in the source code, it says if n is 0, malloc returns a minimum sized chunk. And we saw that in 32-bit version, the minimum size is 8 bytes. The 64-bit version, let's see, did we show here? So this one should kind of show that. So it's 32 bytes to the next pointer, and the metadata is 16 bytes, which means the minimum is 16 bytes. You ask for 0, malloc actually give you 16 bytes. So this is a lot. Okay, so the point here is the malloc chunk size is bigger than the buffer size. And not only because of the metadata, could also be alignment as well. Okay, then let's look at those fields, especially when they are, this one is when they are in use. Okay, so we have a print chunk function. Input of that is a pointer, that's the buffer pointer. Then also the size of that chunk, that buffer. We print out the previous field, okay? But first, let me show it. It's right here. We first print out the previous field. Like I said many times, this one is not really used in current version. Then we print out the size of it. The size of it, the last 3 bits is not really for size. That's why you will see some weird thing at the lower least significant bytes there, but not really matter. Then you print out the buffer size, which is, so this one maps to this one. This is the first one, the previous one is just the buffers pointer minus 2. Okay. This one is just the buffers pointer minus 1. One item, okay, which is 8 bytes for 64-bit machine. And then we print out how many we asked for. Then we were asked for 0, 4, 8, 16 to 16K bytes. So that's how many of them? I don't know how many. So that's what we asked for. Then we just malloc them. Then we just print out the chunk. So let's take a look at the output. Let's just do 64-bit. So this is the output. You can see for each chunk, the previous field is just 0. It doesn't indicate the size of previous chunk. It's just 0. Then the size field indicates its own size. But the lower significant bits are a little bit weird because the last 3 bits have special meanings. We will not get into, doesn't really matter for this class. Okay. So, but roughly you can say the first one is 20, right? 20 is 32 bytes. 20 in hex, so that's 32 bytes. We malloc 0 there, we get 32 bytes because 16 bytes of metadata and 16 bytes of buffer, right? Then we malloc 4, we also get 32 bytes. 8 up to even 24, we get 32 bytes. So that 24 probably using some bytes from the next chunk. Then even larger one, this one. We can say that the previous ones, they are continuous. We can say this one here, so here, they're probably continuous. So from here to here, I think they're still continuous. From I to B, still continuous. Then from B to F, still continuous. Then this one, I'm not 100% sure. Yeah, I think they should be continuous. Okay. X calculator. We use. Yeah, I should print that out. Where's it? This address to. Yeah, so you can see the decimal value here is 4,000 something, right? 4,000 something, and we were asking for 4,000 something. So there could be a little bit of alignment, which means they are still continuous. So one after another. So each of this is created by splitting the top chunk. So they are still continuous. So there, I have a screenshot for 32-bit version and 64-bit version. Let's see. Okay. So then let's look at the freed one. The previous one we looked at was in use, the malloc one. Okay, so now we free them, and they go back to the singly list. We have a new function called print freed chunks. The previous function is print in use chunks. The difference is in the freed chunks, we have two more fields. The next field to the next available chunk and the key field point back to the structure. So for the in use chunk, we don't have those two fields. Those areas are used for your application data. That's for buffer. The free one, we have those. So we first malloc 5 chunks. All of them are 32 bytes. Then we print the in-use one. If we call print freed one here, where those two fields will not make sense. Okay, so that's why we didn't call print in use. Then we just free each of them. Then we just print out 3 chunks. So let's see the result of this one. Okay, we first malloc 5 chunks. The previous field is 0, expected. The size field is 30 in this case, 30 in hex, which is 48. Okay, 32 bytes, what we asked for, 16 bytes for metadata. So in total, 48 bytes, 30 in hex. Then we have the buffer's address, the chunk's address. The buffer's address is, the first one is B0, 16 bytes before that is just A0. Okay. So the chunk basically is the metadata address. Then we free all of them. Okay. After we free them, they should go to one list, right? Because they have the same size. They should go to the same bin, the bin for 32 bytes of chunks. Okay. So the first one, after we free them, the first one, this one is, we free them one by one first, then we print out each of them. So technically, we are printing out some memory we have already freed. Okay? So this is a use after free bug here. The first one is what we freed first. Okay. However, after we free it, we didn't print this out. We free the first one, second one, third one, fourth one, fifth one. Then we print them out. Okay. So then the first thing you notice that they have the same. The key field points to the same thing. That's expected. That is what's working. So that is basically the per thread structure. The address of that is somewhere 9010. Okay. That is a. So all the other chunks have that key field point back to that. Then the very first one we freed is printed out here. That's the first one we freed. When we free it, it was the top of this was the first item in that list. But then we freed the other 4. So now it becomes the last item in the list, right? So that's why it's the first freed one. It's the last item in list. So it doesn't have the next one. Okay, so that's why the next points to null. The second one, it was insert between the head and the first one. So that's why the next field here points to. So the next field points to this guy, this chunk, right? Of course, it doesn't directly point to the chunk. It points to the next field. The chunk is the chunk again. Let's say this is low, this is high. The chunk is and the T pointer, which is next, and the key. Okay. So that's why, let's say this is the first one, the first chunk. The second chunk will have the same structure, P, current, next, and the key. So this next pointer doesn't point to here, right? The next pointer actually points to here, to the next pointer. And this is where the buffer is. When you save the data, this is where the buffer is. When it's in use, this is buffer is. Now it's free, it's the next pointer. That's why here you can say the chunk is at A0, but the buffer is at B0 because 16 bytes of metadata. So that's why the next field is actually B0. So this guy actually points to the first guy, right? That's what we expect. Then the third guy, B0 points to the previous guy, and this one points to that one, this one points to that one. So this is a fivefold structure. We free the A first, and the A will go to the bottom or the end of the list. And later when we malloc, we will use this guy first, then this guy, then this guy, then this guy. So that's free. Yeah, as you can see, previous, not used. T point to the same thing, and this guy points to the previous guy. Also, glibc uses the first fit algorithm to select a free chunk. So even if you do not ask for exactly the same size, it may choose the first fit. Do not necessarily always go to split a new chunk. In this example, we malloc two chunks. One is 512 in hex, another one is 256 in hex. They're just kind of random numbers. Then we were free A here. After we free A, we will malloc another 500 in hex. That's 800 bytes. So previously we malloc something a little bit more than that, 818 bytes maybe. Okay. So previously we malloced 818 bytes. Freed that. Now we malloc another 800. Instead of create a new chunk for just 800, glibc will just reuse that 500, a little bit bigger chunk. So I think that's easy to understand. We'll just try to reuse that since their size is similar. So we can, even if they are not exactly the same size. So you can see that it's a little bit busy here. The first time we allocated here, the address is 9280. Okay? We free it. We allocate it again with a different size, slightly smaller. The malloc is giving us the same address, 9220. Okay? It's not creating a new chunk. We're using that chunk. So all of those will be useful in different hacking scenarios. Okay, let's say. So even if you ask for something smaller, some malloc versions will just reuse it, but they may split that instead of splitting the top chunk. So here, we malloc A and B, then we free A, and A is a big one. So A is 800 something. Then we malloc another 256. This is actually more than that because it's hex. 400 something byte. Okay. So instead of splitting from the top chunk, malloc may choose to just to split A into two smaller ones. One of them will be that 400, another will also be 400. We choose to do that. Another example, of ABCD, all malloced at those address, and those are the return address. 97D0, 9860, 9850 of F0, 9980. Then we free ABCD in that order. We free. So order matters. We free them. So now we malloc ABCD again. What should be the value we get here? What should be the address for A again?
D.
So A will get the address of D because this is kind of like a FIFO structure. And B will get the address of C. C will get the address of B. D will get the address of A. Okay. Okay, finally, we get all of those background. We can start hacking. There are many, basically it's 3 different hacking we're going to learn. First one is still overflow. That's similar to a buffer overflow we learned before. Just a little bit trickier. There are many different structures on stack. And if we can overflow them, we can control many interesting things. For example, in the Linux kernel, those kernel credentials, they are on kernel stack. If there is a buffer overflow there, then you can change your credential. Regular process may have the root process, the root permission. We actually have a paper under review to defeat those kind of attack using some hardware signature feature to do that. This is our first example. We have a main function. We have a function called fly here. We're just print out flying. Then we have a data structure here called airplane. The airplane data structure has a function pointer, and it has a buffer. So function pointer is a pointer. So 32-bit version, it will be 4 bytes. 64-bit machine will be 8 bytes. Then there is a buffer, at least 20 bytes. Then we will also print out the print flag function there. We have a print flag function. We first malloc an airplane heap. We print out where the airplane 1 is. We have another airplane 2. The fly function of both of them. Then we do a fget. So that's a traditional buffer overflow you are familiar with. We first overflow this field, name field, of the second airplane. So there's no overflow here, right? Then we get the plane name of for the first plane, 100 bytes. So that's where we're going to flow something, overflow something. So we created 2 airplanes, right? Which one has a lower address in this case? We malloc twice. So stack goes from high address to low address. Heap goes from low address to high address, right? So airplane 1 will have a lower address. Airplane 2 will have a higher address. That's why if we overflow, but when we do fgets, we're writing from low address to high address. Okay. That's why when we do the overflow here, we overflow the first airplane instead of the second. Okay, so I will give you the guys a minute to work on this one. The idea here is very simple. We're going to call P1 function and P2 function, and we are overwriting from here. How many bytes we need to overwrite this, and what we are overwriting. You can work on either 32-bit version or 64-bit version. Yeah, we also print out where the airplane is for you guys. So that will be easier. So, sorry, version. First airplane will have previous size 4 bytes, the current size 4 bytes, the buffer, well, just don't call it buffer, will be the function. Then the name, we don't know the size of this, at least 20 bytes. So this is where the buffer is, or where airplane 1 is. Okay. Airplane 1, the address doesn't include those two. This for you. Then we will have the second airplane, have our previous one, 4 size, 4 bytes, the current size 4 bytes, and function pointer 4 bytes. We also print out. Then you are overwriting from here, right? Because this is the name of the first airplane. You overwrite from here. Then you just need to compute how many bytes this is. Then you overwrite this field to the address of the print flag. That's it. Let's work on the 64-bit version because I show you guys. So you can just run this to print out the address. You don't really need to read the assembly from the disassembly here. Okay. Yeah, so maybe it was in. Or you have to put twice. And then you guys something extra. So here, the program is asking you for two lines of input, right? So the first line doesn't really matter, but you do need to give that. So that's why we have the slash n here. So that's the first line. The second, then you will have, because there are two first fgets, you are not going to be able to overflow anything, but you still need to give it some input. That's why you put a whatever a slash n there. Yeah. So after that, it's what you're trying to overflow. First airplane name. The first one. In working SPT. No. So it takes. The second one.
This keeps sounding like, yeah, I tried putting it in quote.
Wait. Yeah. A slash on somewhere. Say. So slash on. Oh, no. Should so. Right, you should not. This is the truck and the first one. Plus the buffer that I need to over.
Yeah.
Oh, okay. So you don't need like. Yeah, you can do it in one by So there is an example there. So the exploit should look like something like this. So first there is the name for the second airplane, whatever you put there, but you should have a new line there. So this will get the first FGETs out of the way. And after that, we're for the second FGETs. Okay. I'm not sure 40 here is correct. You need to compute that. Then it will be just the address of print flag. We'll give you the address. One 32-bit. So what is this? It is printing out the name. We're not flying. So sometimes not flying. What did you get? 28? This one minus this one? That's 28. Let's say airplane 2 to airplane 1. That's so. So what you have here is from here to here is 28 bytes. Yeah, from here to here is 28 bytes. You're not overwriting from here, so you should have 24 bytes. Right? From this one to this one. However, you're not overwriting from here, you're overwriting from here. It's a buffer. Oh. Well, this one, this one. That's 32, right? C0. So this from here to here will be just. Oh, okay. Bit before. So how many buffer? What's the size of buffer?
28 for 32-bit it's 28.
28.
Yeah.
Okay. And over the function address. What's wrong?
That'll be
Those refresh the bunker.
That lower address.
Okay, let's keep moving forward. Okay, then the most interesting part of heap exploitation, obviously not those overflow cases. More cases that utilize, we learned how internally the heap works. Okay, class of probability is called use after free. So probability where the data on the heap is already free, but we still have a pointer to that. So the best practice here is you malloc, then you change the pointer to null. Okay. First, don't necessarily do that. They do not change the pointer to 0 to null. Okay. Then that pointer later may be used again somewhere. When it is null, it is dereferenced, it's used, you get a segmentation fault. But when it's not, you may have some more serious security issue. So here is we have a pointer. That pointer we call a dangling pointer because what it points to doesn't exist anymore. So this is a very popular class of probability in complex programs because they use a lot of heap and they have pointers to doesn't exist data and can be used. So the concept of this use after free is not necessarily just at the heap level. It can be at many other levels as well. Give you another example. You develop a website. Your website will use a lot of libraries. You may use JavaScript. You may use a library like CSS, right? So you do not code them. You just put them in your HTML header. There's a script tag, there's a CSS tag, whatever. But it will point to some other place, not on your website, on someone else's website, which you do not necessarily have control. Okay? So today you develop a website, you point to a JavaScript on someone else's website. Tomorrow, whoever was hosting that website takes down the website. The domain doesn't exist anymore. So you also have a dangling pointer in your web page. So as an attacker, if you find those dangling pointers, what you can do? You create a just the domain name of the previous one. Instead of the previous JavaScript, which is a benign one, you host a malicious JavaScript, right? So this is also a dangling pointer used after free problem. Right? So the concept applies to other levels. So how do we use this at the heap level? The idea is simple. We have heap, we have stack. The heap, we have different chunks. This is the first chunk, second chunk, third chunk, fourth chunk. Then there are pointers pointed to everywhere. There could be a local variable on stack points to somewhere on the heap. There could be a heap object has a pointer inside the heap object has a pointer pointed to global variable or pointed to stack, right? A complicated program can have very complicated those pointer relationships. So here, let's say on stack, we have a pointer point to this object, but this object is already freed. It is something else. And then attacker may place a new object there, which behave differently. And then we have unexpected results. So to exploit this, usually you need to allocate a different type of object over the one you just freed. But their size should be the same or similar, so you know where the address, where that object will be allocated. So the second example, we will do 32-bit. Oh, it's actually two different examples. Three. Oh, yeah. The first two, we can do 32-bit first. The last one, we can do 64-bit. a little bit more complicated example than the previous example. We still have the airplane, the same object as before. There's a function pointer. There is, then I have a car. The car doesn't have a function pointer. It only has a volume, okay? It's not an electric car, obviously. It has a volume. Then it has a name, okay? What's important here is those two, they have the same size. Airplane, it has a function pointer, 4 bytes, 32 bit. The volume here also 4 bits, right? 4 bytes, sorry. Then there is a function called flying, and there is also print flag in the address space. We first malloc an airplane for you. Then we set the function pointer fly there. Then we call that function. Right? So out fly. Okay. So we set the function pointer. We call it. After that, we free this. Okay. After we free this, the good programming practice should be we set p to 0, right? Okay. Good developers should do that. But if you just check in the wild, many people don't do that. Now after that, we malloc a car again. Okay. We already learned how this heap works. So it's guaranteed that the car will get the same address as the airplane. Okay. So now we define a volume. Then now it will ask you what is the volume of the car. So you get a chance to input the volume of the car. After that, so here the car has a different pointer, P1. After that, let's say you cannot do P1 P-func. Okay? This doesn't work because P1 is a pointer to the car. Car doesn't have the func pointer function there. If you do this, the compiler will stop you saying there is no function for this type. Okay? However, you still have the old pointer P, which points to an airplane. How does it point to the same address? Right? Now you call P the function P-func. Then you're free again. Free doesn't matter here. So here you are printing out this. You're calling the function. So this pointer points to an object that doesn't exist anymore. That's why it's used after free. So your hack here is to you have a chance to override this function pointer, but you can only override that as a volume. So that's it. Try to do that. It'll be another 10-15 minutes to do this. So the 2-bit version will be fun. This is Second one will be a little bit trickier. We can wait a little bit. Yeah.
That's a basic. Yes, but the thing is that so literally just right back.
Right, the decimal, I guess, right.
Yeah. Because it was the variable n as like this number right here, just add in the SPI. You don't even need to find this because
The second one is a little bit trickier. UAF 2. We still have the airplane, but the structure is changed. We're still working on 32-bit. There is another function. Then we only have two fields. The first field is a long volume, which is 8 bytes. So those two 8 bytes, this one 8 bytes. Okay. But you only get one chance to input the volume. Okay. So you don't really care about what you write into model. You care is what you write into pfunc. But you have only one chance to do that. You have one chance to input 8 bytes, and 4 bytes of them doesn't really matter. So how do you input that? We can switch it.
Yes, I think it's. Usually, that's what I was searching. Yeah. Oh, right, because it's just.
Yeah, it's asking.
aligning to
Yes.
create.
Yes.
Whatever it's, you put.
Oh,
Got it?
Your input should be decimal. You said a scatter only takes decimals included.
Yes. So not raw bytes, but decimal string.
Okay.
Yeah, it's decimal strings. Scav is also a format string function. And that format string there, U means unsigned decimal string. Sorry. Here's the no, no, yeah. Have you got this one already? Alright, good. You should go forward, so it's X first. And have another 4 bytes, which you don't care, then convert that into. You're trying to. It's not going to work. Yeah. If you haven't got it, then keep working on it. If you got it, then we take a break. We come back maybe 8:20. I'll have a number here, right? Okay, this 4 bytes is correct. How about the 8 byte? There, it's looking for 8 bytes, not 4 bytes. Yes, if you just include this, it will be 4 bytes, and then obviously the lower. So the model. Model. What you input there is basically the higher 4 bytes will be 0.
Like difference, like if you didn't have a view for a subject for a curve, then words I would like please do not have like extension breaks or anything. Renovations in my house. These people literally use and keep going.
Yeah, it's only water.
Mm.
Like most houses have portable heat, because they look like very small amount of lights, but having a candle.
For whatever reasons, like FIs is
They try to put like LED Wi-Fi lights.
ready for the class. Yeah, it might have. This is what you have to manage my lecture.
Yeah.
Get the viewing is. Yeah, we can like we can other things not really.
Okay, next one. Let's see this one. So this one is different from the challenges where I've been solving so far. You don't need to input complicated things. You need to find the correct order to hack this. So I'm not showing you the everything of this program, but you don't need to say that. We only need to say some cases, just a particular case here. Okay. So this is a use after free vulnerability we have here. There's a menu. There is a big loop to just ask you what to choose. If you choose one, we'll malloc some memory and it will ask how big you are trying to malloc. Then if you choose two, it will print whatever you have in your buffer, what you just mallocked, okay? Then there is another one case called a read flag, case 3, and I'll give you the source code here. So there is a global variable called secret, that's a pointer. That will malloc 80 bytes. Then the address will go to secret. Then it will open the flag file, read 80 bytes from the flag file, and put that 80 bytes in secret. That's it. Okay. So when you do read flag, it cannot read to your malloc area directly. It will only malloc to. It will only read to. When you do read, it will malloc. Then read to there. Okay. There is a free chunk. You can free your own chunk. then you can exit. That's it. So how can you get the fact of this? Anyone got it so far? Okay, got it. Okay. So this is use after free, okay? So in use after free, you have a pointer point to a free area. So what is that pointer? You do not say that variable here, but that pointer should be whatever you malloc, right? So let's say you first malloc, then you ask you how many bytes you want. You say 20 bytes. Then you just print that 20 bytes. What do you get? Nothing, because you do not really put anything in there. Then you can read flag. Then it will read to the secret, which is malloc here. Has nothing to do with what you malloc there. Okay. Then you can do a free your malloc area. Has nothing to do with this. Malloc again, maybe. Then malloc another 20 bytes. You get the previous block. Okay. So still not going to work. Okay. So the key here is you need to somehow, or because the print will only print your malloc, the area. Make sure when the secret is mallocked here, it's actually mallocked of area you control. Okay. How do you make sure you malloc area you control?
First we choose the first option.
Okay, so you first malloc. So what is the size you should malloc there?
8 bytes.
Okay.
Then free.
So after you're free, what happens?
Secret to be malloc.
No. After you're free, what happens? Under the hood. You malloc first, you malloc 80 bytes, right? Then you free it, it goes to the vault, right? The list for 80 bytes, right? It will be at the beginning of that list. Then what do you do?
Then you do the read flag option.
You do read, then it will malloc again,
Secret is
but this time it will malloc
secret.
the secret, but the secret will point to which malloc chunk it will use. Exactly, it will use the chunk you freed, but you still have a pointer to that. Then what do you do? So that's why this is a use after free, yeah. I understand. So I understand. Okay. Where's the malloc 80? See that? Yeah. So you should malloc 80 bytes first. Yeah. Then you free that 80 bytes. So in that picture, that's the case. Yes, by this. Yeah. Right. but private hard, you have a pointer. Have a use, you have a pointer, let me just print. Okay. Yeah. Read the flag. You try to read the flag. Yes. Do that. Yes. Print my own chart. Yeah. Because you have no pointer to like. Read it. Yes. Okay, let's move forward. We still have a lot to cover. Also, there are double free bugs, but some of them have been fixed recently. So this is an example. What is double free? You just freeze that twice. We'll see a concrete example later. So here, let's say we malloc areas. Each of them is 8 bytes. Then we free 7 of them. Then we malloc or calloc here again. Then we calloc again. We calloc again. So we're going to, we free all 8 of them, for not 7. So we're going to get ABC in use. Then we're going to free A, free B, then free A again. Okay? So the problem here is we freed A twice. Okay? So without that double free mitigation mechanism, A will appear in the list twice, a single list twice. So head will point to A, then point to B. A's next will point to B, B's next will point to A again. Okay. Then A's next actually points to B, so there will be a circle there. But what important is A appeared there twice. Okay. Then when we do ABC again, we do ABC malloc or calloc again. We think we are supposed to get 3 different regions. However, A and C will get the same region. So that's a problem. So that's a bug in older systems here. I think our system probably didn't really check. I will double check if our system have this problem still. So you can say the first calloc and third calloc will have the same address. E3A0, E3A0. That's not supposed to happen. So how can you utilize this to do something more dangerous? So this is an interesting one. This one, to insert any memory we have. In this particular case, we'll insert some memory on the stack to the freed list. So later, when a malloc is called, a stack area will be returned. It can be a stack area, it can be a global variable, whatever. So attackers can control what we are feeding into the free list and later be used. It will not really be in a heap anymore. Okay. So how does this work? At the very beginning, okay. we have, let's say, we have 8 pointers malloc. Okay, we malloc 8 times. We also, so here is actually have a oh 7, oh 7, not 8. We malloc 7 times, and each time is 8 bytes. We'll have 8 malloc chunks, 7 malloc chunks here, right? We free all of them. Now all of them will go to the freed list, and they are on the same list for the size of 8 bytes. Same list. Stack variable, just a local variable. We just want to show that it's a stack variable, so we name it a stack variable. Then we will calloc 3 times ABC, and obviously those 3 times we're going to use the malloc blocks we just freed. We freed 7 of them, right? So now we are using 3 of them. So the list will look like, so let's say this is a heap. We will have, after we do that, we will have 4 free ones. We will have 4 chunks, and this one will be 0, right? Then we will do free ABC, free ABA again, right? Locked ABC, we freak ABA. So when we freak A, the first time we freak A, free A, we're going to insert A here, right? The second time we free B, so it will look like this: B and Z, B to A, right? Like this. Then we free A again, look like A, B, B, but A will actually points to B again here. A's next will be B, right? So it actually becomes this. So those actually are lost. And now the list looks like this. This is error. This is not supposed to happen, but it looks like this, right? A points to B, B points to A points to B. Of course, you can also draw it like this. Either way is fine. This is actually more clear. This one shows you A will be used first. Now we do so we're here. Calloc, and this one we call it D. Okay, which is A. Okay? So now we have a D, same as A. And A will be removed from this. Now it looks like this. B. Okay. But B still points to A, not points to B anymore, not necessarily. But B still points to A, right? Because we didn't change the next field of B. Right? Then we will calloc again. So here, this printf. Attention to this, there is another calloc. This calloc will return B, right? So B will be moved out of this. Oh, the head points to A again. Okay? A will point to some garbage because A is probably in use. So technically A right now is being used. So technically A do not have a next pointer, technically. Okay? Then we have a local variable here. We just set its value as some value, like in this case, 32, which is the size of the smallest malloc chunk here. We're going to use this as size. But this stack variable, it's actually on stack. Okay, this is a local variable. This is how big is this? So this is long. So if it's 32-bit or 64-bit. So 64-bit long will be, let me just say 16 bytes. May not be. No. 8 bytes. This is 8 bytes. Yeah, that's still 32 bits, so this will be 8 bytes. Then we are going to change D. Say D is the same as A, right? So we're good. So D is the same as A. The difference is when we change D, we're actually changing A. So we're dereference D here and changing so we are getting the address for a variable. This is the address of the local variable, right? Stack var, that's the address. We're getting the address of it. Then we use this address to minus the size of D. So this is a local variable. Let's say this is high, this is low. This is a local variable. We are getting several bytes before that. Okay? And we are saying this is a pointer. Okay? And this is the current size. Okay? And this is size, 8 bytes. The value here doesn't matter. We don't care. Okay? But this value matters. That is the current size. So current size, the buffer will be after this. We're only creating this local variable, this part here. We're getting this and use this address as we use this address to overwrite this D. So then D will be, then after that, basically A and B will be, because A here actually will be the next one. So the next field. So the next field of A is overwritten. So it will be -8. Anyway, you were pointed to this structure, right? So now we created a structure on stack, and we somehow insert that to use the next pointer of A to point to that, and A is still in the free list. See? Okay. So previously A were, if we consider this as there's a next pointer, it will point to some garbage. And now it will point to our local variable. After that, we calloc again. And this calloc, basically here, is where pointing to our stack local variable. We calloc again, and this one will take A. Then our stack variable will be our next. So when we do malloc again, here, we are going to malloc the address from the stack or anywhere we control. Not really a memory region in the heap anymore. Okay. So the fourth one, this malloc, this calloc here will actually return the stack address. Okay. So this is possible because of this double free block here. Okay. And the key pointer we talked about is used to defeat this kind of attack. Because whenever we want to free a malloc chunk, we are trying to set the key there. The next time we free it again, that key field should already have this value. So when we do this free here, we will set the key. When we do this free again, it should already have that key value. Then Heap will stop us by doing that. It will show double free detected. Okay. So that's how it stopped. So I think our server version is not vulnerable to this one anymore. I will double check this weekend. So this is double free. So the same concept works for many different kernel architecture structure as well. So there have been a lot of attacks on memory page tables because those are also some of them are also on the kernel heap. So use double free, use after free to attack those. And some interesting attacks there. So on a machine I used before, this is the result. The first malloc, you can see it's 5.6 something, that's a heap. The second malloc, heap. Then we free it twice. We free it once, then free it twice. Then we change it to point to the tank. Then we do malloc again. An unnamed one, I guess. Then get rid of B. Then this is the third one. We get rid of A again. Then the fourth malloc, we get the stack address. You can see the address is 7F. This is obviously not a heap address, but we somehow put that onto the free list. So this is a double free. This is also a class of vulnerability. There are many other attacks, but they are not really effective anymore. So that's why I call them historical attacks. I guess we can skip those because they are not that relevant anymore. I'll just give you some idea of this. So especially some of them use double linked list before. The idea is, so a previous version, when you have two chunks here, you have chunk B, A, B, C. B is already free. Then you have chunk A there. Then when you free chunk A, the program, the heap, memory allocator will try to merge chunk A and chunk B, merge into a bigger chunk, okay, to defeat memory fragmentation, whatever the purpose is. And their implementation had a bug before it. So this was the implementation before. The implementation was using two macros. And those two macros actually can be manipulated. So this is basically the vulnerable function macro there. Trying to unlink one is basically to unlink is try to use a chunk. Those chunks, they are free. They are in the list. To unlink them is to remove them from the list. So we are trying to use it. Okay. So the idea here is we have, this is a double link. So it's different, it's previous edition. Chunk A has a forward pointer, has a backward pointer, the previous size and chunk size. So the forward pointer points to the previous, points to the next chunk. Let's call it chunk P, and it will be the beginning of this. Then chunk P points to the next one, will be chunk 3 there. Then chunk 3 will point to the previous the backward one will point to the P. The P's backward will points to chunk A. So this is a double link. Problem here is this piece of code, those 4 lines. For current chunk P, this one, BK, this one, will be changed to what P BK is. The forward one will be changed to what the forward is. So basically to remove this out of this chunk, this link, right? Then the forward one, this one's backward, so now points to chunk 3 and whatever it should point to what this guy's previous points to. And the backward is a chunk 3's forward pointer should point to what his forward pointer pointed to fully remove this chunk from the list and fix its 2 adjacent chunks in the list. Right? The problem of this is if attacker, from attacker's point of view, you are giving us 2 opportunities to overwrite 4 bytes to a location we can control. Okay. Let's say we control this chunk. We control this chunk, then we can control what those 2 pointers are. Because we control the whole thing, we override the whole thing. Then those are 2 pointers. For this pointer, we can control some fixed offset from this pointer, what it's going to be right to. For this pointer, we can do the same thing. So give us 2 opportunities to do arbitrary write. And we only need to control our own chunk. So this is a arbitrary write vulnerability there. It doesn't work anymore. So this is an older version. The double free had a problem. This is still the double free. So this is like I said, Heap is actually a beast. I show you guys a link here if you are into this, you want to dig deeper into this. I have a link. Yeah, this one. Just use this link. So Sharefish is a hacker team from Arizona State and UCSB, one of the greatest college hacker team. So they have this how to heap tutorial for all kinds of heap vulnerabilities for different versions. So every subversion, they create one. And some of the attacks only work for a specific version. That's why every version can say be different. So we're doing this one. There are many different in just 2.31. We only talked about several of them today. Okay. So if you are into this, this is where you can go. If we talk about this, it can take half of the semester to talk about all the bugs. And some of them have been fixed. Cool. So there's another thing I want to really quickly explain is risk conditions. So this is a bug we haven't been talking about. So in system class, you learned about concurrency, and this is related to that. In system class, you think about how to address concurrency issues. And in risk condition, as an attacker, you try to exploit those conditions. So this, when there are multiple operations, try to access some kind of a shared. The shared resources can be a file on the system, can be a file descriptor, can be a memory location. If it's a file, it may work across different processes. If it's just a memory location, it may work across different threads, right? Then the outcome will depend on some timing and the interleaving of the operations. So it's not really deterministic. It's also called undefined behavior. Right? If it works out, you can privilege escalation, data corruption, bypass all kinds of checks, and those kind of bugs is very difficult to detect. I think Rust tries to address this problem at compiler level, but in general, for other programs, it's difficult to find those problems. So one classic pattern for this is something we summarize as time of check to time of use attack, or top-toe attack. Okay. This happens actually for every check in your system. You always check your permission, then later you will use that permission to do something. And those are two different operations. So there is always a time gap. Could be a very small time gap. Okay? If there are just two instructions executing after each other, the time gap can just be nanoseconds, right? However, the attacker can play some tricks. What if you execute the first instruction, finish the checking, then the attacker schedule your process out, the attacker do something to change that check, then later your program is scheduled again to execute, and the condition already changed, right? Of course, there are either cases like there is just a longer time between the check and the use. To exploit this, you need to identify where's the check, where's the use. How can we enlarge that timing window? Sometimes we just keep trying. And so here's one simple example. This one is very simple. This one uses a local file to do this. The main function, there is local variable. There is a string /temp raise flag. That's just a file in the temp folder. Then the program is trying to check the status of this file, the temp raise flag. First, this part checks if this file exists. If this file doesn't exist, it will return 1. Okay? Then it will check if this is a symbolic link. If it is a symbolic link, it will also just return 1. Okay? However, if it is not a symbolic link, it will keep running, and it will sleep for 20 seconds. Just to make this easy for you to attack, I sleep 20 seconds. Okay? In real world bugs, they will not sleep 20 seconds for you, but there are many methods you can use to make it somehow sleep there. Okay? So after it checks this, we're going to open that file, read the content, and print it out. That's it. So when you run this program, you create a local file like that. Then you can put some content in that file. Then you will read the file and output that. You cannot get the flag, right? So the idea here is very simple. You are going to change that file into a symbolic link to link to the flag. The check here is that cannot be a symbolic link. If it's a symbolic link, it will exit. But the check and the read, there are 20 seconds there. So as an attacker, you first create that raise flag file, put some garbage there. Then it checks if it's a symbolic link. It's not. You print out the looks safe. Then in the terminal, another place, or you write a program to quickly change that file, symbolic link, and link back to the flag file. Right? The program is awakened, keeps running. It opens the file. Now it's not opening the original file. Instead, it's opening the flag file and print out the results. So that's why it's called the time to check to time to use vulnerability. And you can say this is a ubiquitous problem because all the checks we have technically they will not happen at the same time as you use it. It will always then you use it, and there is always a timing window. So attackers can try to somehow enlarge the timing. So this is basically the risk condition. So this kind of so all the attacks we have learned so far, we are mainly using user-end applications as example, but the same techniques apply for kernel as well. It's just the interface for the kernel would be smaller. The attack surface will be smaller, but they have the same vulnerabilities we have. So if you look at this, this is a very good repo to summarize all the kernel vulnerabilities. Also papers related to that. If you read those papers, you will find out many of those attacks use the same or combine many different techniques we learned so far. Risk condition with heap exploitation, and also with buffer overflow, with format string, with many different bugs. So real-world bugs are much more complicated than what we saw in the class. That's why you need to combine multiple techniques together. Okay. So next class, we will talk about how to automatically find those bugs. So far, we've been talking about how to exploit those bugs, and how to identify those bugs has been the easy part because the programs we're looking at is very easy, right? Just 10 lines of code. You look at that, you clearly see the bug. By human eyes, sometimes you cannot really see the bug. So next class, we talk about how we use automatic approaches to automatically identify those bugs. Then we only have 2 more classes, actually. After that, we'll talk about cache, and we're done this semester. Cool. Any questions for today? The homework today will be raw. So what we learned last week? Yeah. So the homework this week will be raw. Then I need to update the homework for those ones. Cool, that's it.